5, 4.
Hello, and wherever you are, welcome to the 32nd Orkney International Science Festival. After the dark years of COVID, our aim is to bring the light back. And this evening, we're shining the light on Sandy, on Stromness, and across the Atlantic in Kansas. And our first guest is actually traveling back in time. He's going back 2,000 years. His name is Vasilios Spathopoulos. He's in Sandy, in fact, an island which has many stories of the sea, many legends of the sea. And he's telling about a computer that was built 2,000 years ago and brought from the wreck of a ship in the Mediterranean. Vasilios, welcome.
Hello, everyone, and thank you very much for your introduction, Howie. Thank you very much for inviting me to this year's Orkney International Science Festival. Hi to everyone from the wonderful island of Sandy. 2022 is Scotland's year of stories. My story will be coming from the depth of the Mediterranean Sea, where about 120 years ago, a device was found, the remnants of a device were found that changed the way we see the history of science and the history of astronomy in particular. But before I talk about this device, if we go on to the next slide, I'll recap a little bit on what Howie was saying about myself. I have a PhD in aerospace engineering. That's my background. So I'm not actually an astronomer, but I have a great interest in astronomy, and in particular in the history of astronomy, and have researched it a lot in recent years. I currently work for Glasgow International College, which is affiliated to the University of Glasgow, and I teach engineering, physics and maths modules there. I have a great interest in science, engineering and education, and I have authored several textbooks and popular science books as well. In the last few years, I've been lucky enough to have been awarded a fellowship and several outreach grants in order to create and deliver materials and workshops for astronomy outreach. So if we go to the next slide, can go back to my story, some basic facts. First of all, the remnants of what is now known as the Antikythera mechanism were found on an ancient shipwreck off the island, the Greek island of Antikythera in 1901. It was Greek sponge divers that found this shipwreck by chance. The actual device, that was the remnants of the device that were found, have been dated to between the 2nd and the 1st century BCE. Now, at first, scientists hadn't actually realized how important this finding was. One of the reasons was that they did not have the technology that then came to be extensively used, technology such as CT and X-rays. Once scientists started using this type of technology, they were able to see through the fragments, and major breakthroughs in our understanding were obtained. Once the secrets were revealed of the mechanism, it became apparent that nothing of this technological complexity had ever survived from antiquity. It consisted of dozens of gears, dials, inscriptions were found that showed us that this was a device that was used to perform detailed astronomical calculations. In fact, some people have gone as far as to say that this is the world's first analog computer. We go to the next slide, please. What was this analog computer, astronomical computer, capable of doing? Well, there's a general consensus now on its features. There's one or two details that we are still debating and discussing, but we know for a fact that on the front, it would show the position of the sun, the moon, and not only the position of the moon, but also its phase and its motion around the Earth. And most probably, it also would show the position in the sky of the known, at the time, planets. There was a catalogue of a list, basically, of important star events, what we would nowadays call an almanac. So the dates of the rising and setting of important constellations and stars, and planet cycles as well. It followed two different calendars, an ancient Egyptian calendar and also an ancient Greek calendar, which was seen at the back of the mechanism. Fascinating for me anyway was that it could predict the possibility of eclipses using, in fact, ancient Babylonian astronomy. So there was a dial at the back that would tell you whether there was going to be an eclipse on a particular month or not. Astronomy at the time was very much connected to society and everyday life. So there was a dial on the mechanism that showed which ancient games took place in a particular year. For example, if it was a year for the Olympic Games, this would show up on the mechanism. And finally, like any good computer, it had a user manual and its covers where the functions of the mechanism were explained. So if we go to the next slide, what is my very humble contribution to all of this? Well, first of all, I have developed some online materials that you may want to look at on my personal website, mysciencewalks.com. It uses this set of resources uses two software platforms. Stellarium, you might not be so familiar with. It's planetarium software. It's free to access, and you can either use a web version or download it. And as I said, it functions as a planetarium, and also there's Google Earth. You might be more familiar with that. So you can access these materials and learn more about the mechanism online. Also, as far as the Science Festival is concerned, I've been able to purchase some models. One of them is actually real size of the mechanism for astronomy outreach. I've brought them with me here, and on Saturday at the family event at 10 o'clock at Kirkwall Grammar School, whoever comes to this event will be able to have a look at the models of this wonderful machine. I've already presented at a couple of schools, one in Kirkwall and one in Sandy, but I think it's a great opportunity for anyone to have a look at these models if you have the chance. So finally, if we go to my last slide, please. None of this would have been possible without a small grant, a small support from the Royal Astronomical Society, and I would very much like to thank them for providing this opportunity. Thank you very much.
Vasilios, that is absolutely fascinating. And could I say, first of all, to everybody watching and listening, you can ask a question direct to Vasilios or indeed to the other speakers this evening. And there's two ways to do it, and this is one of them. It's a new system we're trying out this year. It's called Slido. Now, if you have your phone around just now, all you do is you scan this QR code, or alternatively, there is the Slido website, and you enter the code 343, and then all will be revealed. We'll come back at a couple more points in the program just with a reminder about this. You also do have the YouTube chat system as well to put questions, and indeed one has just come in from Richard, a listener in Murray, who asks you, Vasilios, how did you personally first become interested in the computer?
Okay, yeah, that's a good question. Well, I've been interested in astronomy for quite a few years. I kind of try to teach myself the basics. The mechanism itself is actually very famous in Greece. I'm half Greek myself, so it's very famous. You can, if you're ever in Athens, you can go and visit the National Archaeological Museum there, and you can see the fragments displayed, and there's a whole room that's dedicated to the Antikythera mechanism. So I think one of my first inspirations was a book written by an author called Jo Marchant, I think her name is. It's called Decoding the Heavens. It's a very well written book. It's also quite well known, and it's about the Antikythera mechanism. I read that a few years ago, and I think that's what got me started. Since then, I've read another one or two books, slightly more technical. The one I mentioned originally is more in layman's terms, and I've done my research on it. I've become obsessed with the Antikythera mechanism, I have to say. But I think, yeah, one of the first things that got me started was reading that particular book.
And one of the remarkable things about this is we have a kind of image of the ancient Greeks as philosophers, as people very much involved in theory, as compared with the later Romans, who were much more engineers and practical. But in fact, this is showing that the Greeks were masters of technology.
Yes, that's true. what many people don't realize was that there was a particular period, it's called the Hellenistic period, starting shortly after the conquest of Alexander the Great, where this is when ancient Greek culture, by the way, came into contact with cultures such as the Babylonians, the Egyptians, etc. And during this time, the Greeks, the ancient Greeks, actually invented a lot of practical things with practical applications. There were some very famous such scientists, such as Archimedes, for example. He lived at this time. Most of us know him from school, the Archimedes principle, if we did physics, but he was also very interested in inventing things like levers, various screws, pumps, that kind of thing. So he was the most famous, but there were others. There was a guy, if I remember correctly, called Hieron of Alexandria, and he had invented something like a steam engine way back then. And there were several inventions of this type during this era. So the ancient Greeks we should maybe give them some more credit for their practical abilities as well as their theoretical ones. In fact.
We have a question from Melissa, who asks, will the Antikythera mechanism be on display after the festival ends?
Well, I wish I could say yes to that, but unfortunately, I'm based I live in Edinburgh. I work in Glasgow. I live in Edinburgh. So after the festival, I'll be taking them back with me. I'll be using them for a lot of outreach, I hope, at other schools. But I honestly hope to be back again soon, if not next year, maybe, even before that. And I'll definitely, if there's an interest, I'll definitely be bringing the models again. So don't worry about that.
And John asks if you think that the Antikythera mechanism was unique, or do you think there could have been a few more in existence in ancient times?
Well, that's a very good question. I often get asked this question. Actually, I can't remember in which paper, but there is a paper that I read where someone had found that there's 18 references in historical texts to mechanisms like this, who seem to have been similar to this. So I don't think it was unique, and I don't think most scientists that I've studied extensively believe it was unique. But on the other hand, the fact that it was mentioned by historians, or these type of machines were mentioned by historians, means that they weren't. They were owned by a certain type of person, either someone very famous scientist or astronomer that might have wanted to use it for tuition. That's one of the theories for the Antikythera mechanism, by the way, or some very rich person who wanted one for his, I don't know, for his bedroom or whatever, to have to show off. So they did exist. I think was more than one, but I don't think it was your everyday smartphone type of device. I think it was a little bit more rare than that.
Another question's come in from a listener in Murray who'd been following what you'd been saying about the remarkable discoveries that had been made already. And he wonders, do you think there are more to come?
Well, I hope so. We are learning new things all the time about ancient technology. If you're interested in that type of thing, there's actually a museum in Athens dedicated to ancient Greek technology. It's called the Museum of Ancient Greek Technology, and there's a whole lot of inventions there from the ancient Greeks. Yeah, I mean, you never know. Archaeology is something that's at work continuously. So new things could be unearthed that we don't know about yet. In fact, if you think about the Antikythera mechanism, we didn't know that the ancient Greeks could use gears, such complex technology in gears, until we found the mechanism. In fact, before the mechanism was found, the next time that gearings like this was used was not till the Middle Ages, when the big astronomical clocks you see in some cathedrals around Europe were designed. So yes, quite possibly there will be more to come.
Vasilios, this is fascinating, and indeed more questions are coming in. But if you can come back again towards the end of the session, we're going to have everybody back on the screen and gathering in questions. So in the meantime, thanks very much. But as I say, don't go away.
Sure. I'll be back. Thank you.
And for those who want to send us questions, here's the magic name Slido again. And you look for the Slido website, or if you're holding a phone, or if a phone's within reach, well, just scan this QR code and wonderfully, it'll take you there and you're able to put a question direct to us. We're going to feature that in all our online events, and tonight's a great opportunity to try it out and see how it goes. But now it is time to move from Sandy to the mainland of Orkney, the town of Stromness. And one of the highlights, surely, of a visit to Stromness is Stromness Museum. It's a museum that's packed full of history of ships, of history of discoveries in various places, of rocks, of birds, wildlife. And also it's an extraordinarily dynamic museum with all kinds of activities and projects. And somebody very dynamic is with us now at the museum. In fact, I see 3 dynamic people, and I think I'm going to ask Katie, first of all, to do the introductions and tell us why you're here and what you're going to do. Over to you, Katie.
Thank you, Howie, and thank you to the Science Festival for having us again, and welcome everybody to Stromness Museum. So we're sitting here in one of the oldest independent museums in Scotland, and Orkney Natural History Society is this is their museum, and it was founded in 1837, so very, very old. And some of these collections in the Natural History Gallery behind us date back to the very earliest times of the society. So not quite as old as the clock we've just seen, but still very old. So I'd like to introduce Connie and Emily today from Stromness Primary School, and they've been working on a project especially for the Science Festival with me, and also the Fossil Centre in Burray, the Orkney Fossil and Heritage Centre there, have been involved. So lots of people have come together to make this happen. So thank you very much to you guys for that. So our project is funded by Museums Galleries Scotland, and the sort of aim of the project is for us to focus on the natural history collections in the museum and to use those to their full potential, because we have such a rich natural history collection here. You can see some of the taxidermied birds behind us, but also just behind Connie are fossil fish. Thanks, Connie. So we have a great collection of fossil fish, and we know that young people love fossils, and we've spoken to quite a lot of primary school children around Orkney over the last year, and they told us fossils and geology is one of their favourite topics. But the thing is, I'm not a geologist, so I had to find an expert geologist, and I was really lucky to be introduced to Emma Bernard, who is here with us tonight from the Natural History Museum in London. Hi, Emma.
Here. Hi, everyone.
Hi. So I can do a little introduction for Emma, and then Emma's going to give you a wee presentation about fossils, and then we have some questions from Connie and Emily, and also from Burray Fossil Centre to ask Emma. So that's the format of our section. So just to introduce Emma, Emma's the curator of fossil fish at the Natural History Museum in London. She has 15 years experience of working in UK regional and national museums, and she's been at the Natural History Museum for 11 years. And I have something in common with Emma because we both studied at the University of Glasgow and had some lectures in the same building even. And Emma's done some really exciting research. She's researched dinosaur footprints in sky using the Hunterian Museum's collection in Glasgow, and that really gave her the bug for working in museums. She's very passionate about outreach and does a lot of outreach events for the Natural History Museum each year. She also does very exciting field trips, which is surely the highlight of being a paleontologist. She's worked in Europe and Africa, and she was part of the Mission Jurassic team to North America. So I'm sure for most kids watching, this is just their dream job, and probably I'm a wee bit jealous as well, Emma, of your job. So over to you, Emma. Thank you so much for joining us tonight.
Thanks very much for inviting me along. It's a real pleasure to be able to speak to you all this evening, and I'm hoping for some good questions about some of the fossils we're going to be talking about. So, as was mentioned, I'm a paleontologist. I work at the Natural History Museum in London, and we're going to be finding out a little bit more about what fossils are, how did they form, and obviously some of my favourite fossils, and that's obviously fossil fish. So the next slide, please. So as a curator, I'm basically, it's kind of similar to a librarian, but instead of looking after books, I look after fossils. So I'm responsible for about 100,000 fossil fish. So I need to know where they are, how old they are, what are they, how did they die. And I work with a number of different researchers from all over the world that want to come to the Natural History Museum to look at our collections. Now, if they're unable to come to the museum, I basically help them with their research. So whether that be taking measurements from fossils, taking images, basically just helping them along. I'm also very fortunate I get to work on exhibitions both inside the Natural History Museum in London and also touring exhibitions that go all around the world. And as it's being alluded to, so one of my, basically my 5-year-old self, very excited about getting to travel the world and dig up fossils for a living. It's not always glamorous because I've done field work when it's been -5 and snowing, and to when it's been about 45 degrees and very dry heat, so and everything else in between. But what's really special about doing field work is that you're the first person to ever set eyes on that fossil. So that's really cool and very exciting. And also one of the things I'm very fortunate, and one of the highlights of my job, is about doing outreach and speaking to people about the work that we do in the museum, and also some of the research that I'm involved in as well. So you can see that my job is very diverse, and I get to be involved in lots of different things, which is quite fun. So I thought we would start off with basically, what is a fossil? So I mentioned that I'm a paleontologist, and that's basically a fancy word to describe someone who looks at very old dead things. And basically, the simplest sort of phrase, and there's many different definitions of what a fossil is, but basically the simplest definition is evidence of past life. Now that can take many different forms, and the most common one that you'll probably think of if you think of a fossil is probably a dinosaur. So we've got a dinosaur leg here, so part of a sauropod. We've got fish, we have shark's teeth, we've got trilobites, coral, shells, brachiopods. So basically it's the hard parts of any organism. And moving on, the next thing that we can often come across, although it is very rare, is actually soft tissue. We can get that soft tissue preserved. So here we've got a few examples where we have ink sacs that have been preserved from octopus and squids. And we can also have fossilized leaves, cartilage from fossilized sharks, and perhaps one of the most famous examples are feathers from dinosaurs. I think everybody's aware on films like Jurassic Park, feathered dinosaurs there as well. So this is very, very rare, and we're going to be talking about soft tissue preservation a little bit later. So alongside the soft tissue, perhaps the last type of fossil that you can come across is trace fossils. So if we go on to the next slide, trace fossils, again, we've just got a few different examples there. Most probably iconic one is dinosaur footprints. So these are some from the States. So you can see these three-toed dinosaurs. And from that, we can work out, were these dinosaurs walking on 2 legs or 4 legs? We've also got some fossilized eggs there from a shark and also some other reptiles. One of my favourite trace fossils are coprolites, or basically fossilised poo. And these are really actually quite interesting. As you can see on the screen there, the coprolite that we have in the middle, you can see a little black flecks inside that coprolite. Now these can often be things like scales or bones, so we can look inside these coprolites to work out what these ancient animals were eating hundreds of millions of years ago. We've also got a few examples of some burrows, so those white squiggly lines there that you can see in the rock. That's where an animal like a worm has dug down into the sediment and it's been filled with sediment on top. So moving on, we've got, we mentioned that fossils are typically millions of years old. I know that can be quite difficult to think about. So on the next slide here, we have, hopefully just to, oh sorry, if we go back one, we have a clock here. So think about a 12-hour clock. So at the top, that's when the world first formed. And that's about 4.5 billion years ago. So we actually have to go all the way around the clock till about 10 p.m. until we start to see some of the first animals on Earth. And that's the yellow star that you can see there. Now, dinosaurs, they didn't appear until about 230 million years ago. And that's about 11:25 on our 12-hour clock. And to put that into perspectives, humans, we only appeared about 300,000 years ago. So that's the last 2 seconds before midnight. So quite recently, geologically speaking. So we're going to take a little bit of a time travel back into that, so about 400 million years ago. So that's probably about 10:30 if we were to continue with our clock metaphor. So on to the next slide. The study of rocks and how they formed is called geology. And at the side of this slide here, we've got a great geological timeline I've modified slightly from retro. And where at the top we have present day, and our friendly paleontologists are off out in their truck on a fossil adventure. Now they're off trying to find some fossils, and as we move further down the clock, further down the geological timeline, we move back in time and we go through different geological time periods. Now some of these might be familiar to you, things like the Jurassic period, but if we go even further back in time from the Jurassic, you notice that I've circled there in white the Devonian period. Now this is often known as the age of the fishes. And that's because we can find an awful lot of fossil fish from this time. And there's lots of Devonian rocks in Orkney, and we're going to be talking about a few of those fossil fish in just a few minutes. Now, unfortunately, the fossil record is not complete, so we'll only ever find a small fraction of past life. And this is due to several things. So typically, it's often the hard parts of an organism, such as the shell, bone, or the teeth that preserve, much better than the soft tissue, as I mentioned previously. And most of the time, the animals and plants that we find as fossils actually lived in or near the water. And that's because we need sediment to cover these animals and plants whenever they died, in order to help along with the fossilization process. Because if it's left lying out on land, the chances are that they will be eroded away. Now, even if something does become fossilized in a rock, it can be eroded away once it's exposed at the surface, perhaps due to the waves crashing into the rock. And we only ever find fossils in sedimentary rock. So a couple of examples of that might be things like mudstone, siltstone, or sandstone. And we don't find fossils in igneous rock. So if you think about it, volcanoes are very sort of destructive. So we don't find fossils in things like basalt or granite. So moving on, how does something become a fossil? So we're just going to talk about the fossilization process. So let's talk through this. So there's a number of different fossilization sort of processes depending on the organism and the type of environment it died in. But we're just going to use an example of an ichthyosaur, which is a marine reptile that lived during the Mesozoic period era at the same time as the dinosaurs were busy stomping around on land. That could very easily have been a fish from the Devonian. So the first step we have here, we've got our ichthyosaur. It dies for some sort of reason, perhaps due to old age, or it gets attacked by something else, and it falls down to the bottom of the water. The second step is that ichthyosaur might be partially eaten by something else, or if not, if it's buried very quickly with lots of other sediments, perhaps mud and silt, and being compressed down in something that we call a anoxic environment. So there's no oxygen for even bacteria to come and eat all that soft, fleshy stuff. We can get some of that soft tissue preserved. Now, the third step relies on more and more sediment being built up, and that eventually puts more pressure on the layers further down. And at the same time, there's liquid seeping through the layers and the bones, and it undergoes basically a chemical reaction, turning those organic remains into a fossil. Now, after a long period of time, the next step, sometimes these rocks might be uplifted to the surface, perhaps due to plate tectonics, perhaps the water subsided away, so the rock is now exposed at the surface, and then it's eroded away by the elements. And you might just see a few little bones sticking out at the surface. And that's where you and I can come along and we can dig up that fossil and then prepare that. And here we've got our finally complete ichthyosaur skull. So now we know what a fossil is and how it forms. We're now going to quickly travel back in time to the Devonian period. So on the next slide here, this one, we have basically what the world used to look like back in the Devonian period. And you can see that it looked very, very different to the globe and the world that we're familiar with today. So the Devonian period, we're just going to say about 400 million years ago for this particular one. And you can see here that all the continents are more or less in the southern hemisphere. And what I've done is just to make it a little bit easier is I've circled where the UK is on that landmass. And that landmass was called Laurasia. And over millions of years, those land masses broke apart, they came together, broke apart, they came together, and moved further north into the modern day places that we find the continents. Now, remember, this happens over hundreds of millions of years. So now that we know basically this, where the UK used to be, so much closer to the equator, was it be much, much warmer. Let's zoom in even further. So back in the Devonian period, a massive freshwater lake covered most of what is modern day mainland Scotland and a lot of the islands as well. And this was a big freshwater lake called Lake Orcadie. And this is a great artist's impression by Ian Ashman of what the landscape might have looked like. So as you can see here, the lake is surrounded by lots of mountains, which would have had rivers and streams draining into that lake. Now, this would have been very hot and a mostly arid landscape up on land, very similar to a desert. And there would have been some very early plants and insects up on land. However, the waters were teeming with life, especially fish, and those are the remains that we can see today. So one of the reasons we can find the fish preserved as fossils is because of those river systems that were draining into the lake. With that, they were bringing down sediments, and then as the fish died, so we've got a nice diagram here, lots of different fish living side by side. As they died, falling down to the bottom of the lake, and then being covered with more sediments and going through that fossilization process that I was talking about. Now, this happens over millions of years. It's not an overnight thing. And these are the fossils that we can now find. So moving on, what were these fish? Perhaps one of the most iconic fish that we can find in Orkney belongs to a group of fishes which are now completely extinct, and these were known as the placoderms. So all of the fossil examples I'm using here are all fossils that come from the rocks in Orkney. Now I've labelled the head and the tail here in this specific one, just so you can kind of orientate yourself. And I've also got a reconstruction of what this placoderm might have looked like. Now placoderms had these really thick, dense, bony plates that were all over their skulls, all over their heads. And this is what we typically find preserved, and that's because they were really thick, dense, bony plates. However, the back half of the animal, and as you can see in that picture of the fossil here, we've got a long line of vertebrae. Now, obviously the fish wasn't that skinny, but that soft tissue didn't fossilise very well. So that's why we can see the actual vertebrae of the fish there. Now, some of these placoderms could go to about 25 centimetres, maybe 30 centimetres or so in length. And they had a joint between the neck vertebrae and the back of the skull, which allowed them to open their mouths a little bit wider. And placoderms, they didn't have teeth like fish have today. They actually had bony plates inside their jaw, and they stayed very sharp by opening and closing of their mouths. And that's basically how they fed. So another type of fish that we can find are lungfish, which might be familiar to many people, as obviously lungfish are still around today. And this is a very iconic one, lungfish called Dipterus. And we've got a few skulls there. So this is all from the back of the head, back of the skull of this lungfish. And Dipterus probably would have looked very similar to modern day lungfish. Again, they were about 30 to 35 centimetres or so in length. And it's actually thought that Dipterus could have survived out of the water for short periods of time, suggesting that it lived in quite shallow waters. Now, if you're a fish, that's actually quite a unique and also helpful character to have, because during the Devonian period, this lake was sometimes patches would dry up. So therefore, these lungfish were able to basically move and survive out of the water until the water levels rose back up again. The tail would have been asymmetrical, so that meant that the upper lobe would have been that bit bigger than its lower part of the tail, which meant that it was capable of sudden bursts of speed. So quite handy for getting away from some of these big placoderms that were trying to eat some of them. So the next fish we're going to talk about is one called Osteolepis. And this is from the Greek words that mean bone and scale. And this was a lobe-finned fish. And this was from actually a group of fish which eventually evolved and went on to become tetrapods. So things like amphibians and reptiles, and they moved up onto land. So yeah, that's right, we all evolved from fish that used to live in lakes and the seas, and that group of fish over millions of years eventually evolved proper limbs and went up onto land. Now the scales and the plates on this particular fish, the head, they were covered in a thin layer of spongy, bony material called cosmine. And this layer contained canals that were connected to sensory cells deeper in the skin. And these canals ended in pores on the surface that were probably used for sensing vibrations within the water. Now, there's lots of different fish that I could mention, and I've mentioned several times during this talk how famous the fossil fish are from Orkney, and they certainly do have many claims to fame. Now, this fossil that we have pictured here is now housed at the National Museum of Scotland, and it made the front page news a couple of years ago. It actually shows the oldest known fossilised vertebrate embryos in the world. Now, this was a placoderm fish called Watson-osteus, and the fossil itself was found in South Ronaldsay and is about 385 million years old. So what happened here is, as you can see from the fossil itself, it's very well preserved. We've got all the bony plates from the front of the skull, and then we've got the stomach and the tail preserved as well. Now in the middle, where the womb would have been, researchers actually found teeny tiny little bones of basically embryonic little placoderms inside this mother fish. So we were able to tell basically that this fish, these placoderms, were giving birth to live young rather than having eggs like most modern fish do today. So it just goes to show that even though we've been looking at these fossils for hundreds of years, and there's still much more for us to learn and to find as well. So with each new fossil we find, it's basically about trying to piece together how these ancient animals lived side by side and why they might have gone extinct. So I've spoken a lot about fossils, and I'm sure you're probably very excited to go off and hopefully find your own placoderm fossil containing some embryos. So I've just got a few websites up there that might be quite handy, but please do make sure if you do go out fossil hunting that you take a note of the tide times and make sure that you have landowners' permission, as I'm sure not everybody would appreciate somebody coming along to their back garden and digging up trying to find some fossils in their back garden. So please do make sure that you stay nice and safe. And even if you can't manage to get out there to find fossils, you don't actually have to travel to far-flung places. So on the next slide here, as mentioned, I'm living in the centre of London, and I can guarantee there's not many rock exposures round about where I live. However, just by walking down the high street, I can find lots of fossils in the local shopping centre and down the high street. So here we've got slabs on the floor of our local shopping centre where we can find belemnites, we can find burrows from different worms, and we can also find on cobbled streets some coral and fossilised snails as well. So the next time you go out for a walk or go and collect your shopping, have a look at the local, just down at the in the pavements and the shopping malls as well, because you never know, you might just find a fossil. So I just want to say thank you very much for listening and coming along this evening, and hopefully I've inspired some people to go out there and find some new fossils as well.
Thank you so much, Emma. That was so interesting. I learned loads, and I've got lots of questions of my own. But it's time to go over to Connie and Emily to ask you some of their questions that they thought about along with their whole class. So the class worked together to think up these questions inspired by some of the museum fossils. So I'm going to ask the behind the scenes team to share our first slide so you can all see the picture of the fish which inspired this question. I'm not going to try and pronounce the name of this fish. Can you help me out, Emma, with any kind of description for the fish?
Yeah, so this fish is called
Sorry, I put you on the spot.
Yes.
Tristichopterus
Yes.
alatus. That'll do. So Connie is going to ask the first question. So over to you, Connie.
How do we know what colour the fish were?
That's a really great question, Connie. Thank you for that. Yeah, I'm often asked when people see fossils like these, the image that you have on the screen there, because it's black and the rock itself is brown. So was the fish black? And that's probably not true. To be fair, we don't know for certain what colour some of these fossils were, because often it's not preserved. But what we can do is, obviously fish are still around today, so we can look at modern fish. Where are they living? Are they living in coral reefs? Are they living in lakes, rivers, and the seas? And what colours are they? So often we can see fish that are counter shaded. So that means on the top of the fish along the back, they tend to be a bit darker. And then on their bellies, on their stomach, they tend to be a little bit lighter. Now, in 1997, some scientists found a placoderm from Antarctica. And this was actually thought to be reddish on the top and also have a silver kind of iridescence colour underneath along its tummy. And this was based on the shape of the cells found within this fossil and comparing them to modern day animals and trying to compare those colours and the shapes of the shells. Now, I have to say this is very, very rare, and for the majority of fish, we just don't know. But basically, it's taken well-educated guesses by looking at modern fish. What type of fish are they and how are they living? And then looking at those colours to infer the colours of these ancient fish.
Thank you very much, Emma. That's really amazing to hear about the cells and looking at finding out the colours from that. But as you say, that's quite rare, but we can always hope for our own fish.
Yep, so hopefully Connie can go out and find some fossils that are able to help us along with that.
Yeah, I'm sure you'll inspire lots of paleontologists in the future. So our next question is actually coming from Burray Fossil Centre. So as I said, we have a group who are at Burray Fossil Centre at the moment. We've got Robbie and we've got George and maybe some of their peers from Burray Primary.
Hi there.
And Robbie's question is about this fish here. And he asks, how old is this fish from the Devonian period in between 416 and 359 million years old, an exact age? So I think Robbie's really wanting to know, how can we narrow this down to more of an exact age?
Yeah, so unfortunately, I would love it if all the fossils died with a little timestamp on them when they actually died. But what we can do is we basically look at the fossils, we look at the rocks, and we learn how to read them. And this is one of the great things about science, is that we work with lots of different scientists that have their strengths. So what we can do is sometimes to age fossils is we can look at ash layers. So there's, during geological looking at the past, there's been times where there's been intense, lots of volcanic activity and lots of ash gets pushed up into the atmosphere. Now, if we find a fossil between two of these ash layers, we can try to reduce basically try and work out how old this was. And that's because we can find naturally occurring radioactive minerals inside these ash layers. And by using them and their decay rates and isotope measurements, we can work out the age of these two ash bands. So we can then narrow that window a little bit more. Another thing that we can do is look at the minerals contained within the fossil, specifically looking for isotopes of uranium and lead. Now, uranium and lead, they have, and other radioactive isotopes, have a half-life. And so that decays by fixed amounts over time. Now, if we basically using some very special machinery, we can look to see how much uranium and how much lead is contained within the fossils, and then work out the half-life in order to age these rocks. So another thing that we can use is also index fossils, and that's where some fossils might only live for a very short period of time. So things like trilobites, brachiopods, forams, or nanofossils. And basically, if we find these fossils that we know only live for a short period of time alongside our fish, we can work out that age. So basically, that Dipterus fossil that we have there on the screen, we're able to work out that it's likely to be between 382 million years to 392 million years ago. So about a 10 million window. So it's still quite far, but as technology improves, we're much more likely to refine that over the years.
Super, thank you. And I'm sure Robbie will be really interested to hear all those different dating methods. And I should say that fossil is one of the ones that's in the Fossil Centre in Burray. So our next question about this fish here is over to Emily.
How did the fish become extinct?
Oh, that's a great question. Yeah, so how did some of these fish become extinct? So as with any extinction or animals dying out, there's probably a number of different factors. It's very rare that there's just one reason why a group of animals are completely extinct. Now, at the end of the Devonian period, so between about 380 to 359 million years ago, there seems to be lots and lots of small little mini extinctions, such as due to climate change and global cooling, possibly also meteorite impacts as well, increasing volcanic activity. So basically lots of different factors over millions of years that basically put stress and strain on the environment and the animals that live there. So as a combination of lots of these different factors, we think that's one of the reasons why some of these groups of fish actually then went extinct and died out. So I can't give you a definite reason why this particular fish might have gone extinct, but as with most extinction events, as I said, lots of different factors. So typically because of changes in the environment, meaning that that animal, so this fish, couldn't adapt and change accordingly. So a great question.
Thank you so much, Emma, for those answers, and thank you, girls, for those questions. And also
really great questions, so thank you.
They really were, and as I said before, we worked on it as a class, and I really thank the Fossil Centre in Burray for getting involved as well, and for taking time to have a look at their fossils. And I'm sure there's probably questions in the chat as well, but I think that's all we've got time for at our end. But thank you very, very much, Emma, for taking the time to be with us all the way from London.
Well, that's fascinating. And there's actually, if all goes well, there should be time maybe for even one more question later on. So in thanking you just now, Emma, Katie, Connie, and Emily, I'll say don't go away, because we might have time for a question at the end. And in fact, you'll be able to see our next guest, because it's time to join a real life wizard. To do that, we have to go to Kansas, and we have to do it in a special way. We have to put on an equivalent hat to welcome the wizard. And this is a hat that the wizard very kindly sent us just to make us feel at home with the wizardry in Kansas. His name is Steve Jacobs, known to the world as Jake for short. He's a former chemistry professor. He's the retired chief scientist for the Discovery Channel and for National Geographic Television writing. And he consults, or has consulted, on 20 network science education programs. He has international activity. He was recently on the team developing the vaccine for leprosy. He's currently a member of the UN team developing impact programs for the UN Sustainability Development Goals project. But most important in this context, in 1995, he received the title Wizard 4 from the Royal Institution of Great Britain. And we're going across to the Wizard Centre in Kansas now. Jake, good evening to you, or whatever the time is in Kansas.
Whatever time it is in Kansas. This was becoming one of the best days of my life, Howie. Just before you came on, we were sitting here eating pizza in the studio, waiting our turn, listening about the fish and stuff. It was pretty cool, wasn't it? It was a good day. Well, I'd like to welcome you to, this is Faraday Studio. And yeah, I can't tell you our exact address because we keep it secret, obviously. We're the center of the known universe is what we like to call it anyway. So we're in Kansas, out on the flat prairies of Kansas. And it's where I grew up. That's why I returned here, because it's my home. And I am a chemist by training, but I did get the title Wizard 4. And I thought just for a second, maybe you'd like to see the studio and why. So do we have something we can show them around the studio, Scott? Oh, here we go. If you hear my voice, this is a collection of science materials that have been collected for 225 years. Oh, look, a member of the Faraday Club. That's the greatest thing. We have the world's largest collection of science activities here. Somewhere between 20 and 30,000 science demonstrations that have been on all sorts of media for the last 225 years. And I just happen to be the current keeper of all of this. So there we go. Welcome to Faraday Studio. That's it. Golly, you didn't even, that's where we're at, man. And you'll notice I've got the hats on. This is the home of Midnight Science Club. It's a worldwide organization of Well, I don't know what we should call ourselves. Scientists of all ages. I think we have 5-year-old members and 105-year-old members and everywhere in between, and we all have an interest in science and science communication. And Howie, the reason I'm here today is, one of the words, it's the Orkney, what is it? International Science Festival. And I wanted to hit on that last word, festival. We want to do something festive. So we're going to do some really neat science activities, but the significance of these activities is, I don't know, when did I first come to the Orkney? Was it 7 or 8 years ago? Something like that, and opened it or something like that. Yeah, 7 or 8 years ago. And it had such a profound effect on me, being in Kirkwall with these dear, dear people, and you wouldn't recognize them as scientists. They're just folks. But we went and ate dinner at the pubs, and we went to these sessions, and then you could just feel people absorbing these beautiful bits of science. I thought, man, this is incredible. And I was at the point of retirement. I thought, no, I want to retire. I've done this for I did my first physics lecture, presented in '64. So I thought, it's enough. I'm going to retire. But after I went to the Orkney thing and met Howie and all the people that were involved, I thought, no, there's a little bit of gas still left in me. And I thought, what can I do? Well, here at the studio, we have the world's big collection that was, can you show a picture of the 4 wizards? Oh, we got that picture. We got a picture of us. Not only are they a handsome group of people, but there's Michael Faraday, and he was born in 1791, I think, and lived to be 1860 something or another. And Queen Victoria called him the wizard, meaning the wisest one. It had nothing to do with witchcraft or magic or any of that stuff. And he was Wizard 1. And sitting next to him is Hubert Allier, who was at Princeton. He entered Princeton when he was 16 years old in 1906, I think it was, something like that. And he was such a good communicator. Madame Curie was there for a semester, a guest, and he was her sidekick, helped her around and stuff. And she said, Al, you're the next Faraday, because you can communicate science so sweetly. So the United Nations, UNESCO, later on picked Dr. Allier up to go around the world right after the atom bomb was dropped on Hiroshima to explain to the world's population what atomic energy was. And he fascinated people and eased a lot of tensions just with his casual and friendly attitude about science, and eased a lot of tensions about the atom bomb. And Walt Disney, from Disneyland and Disney movies, saw him at a lecture and made a movie about him called The Absent-Minded Professor back in the 60s. Oh, there's Allier right there. And he was a character, but he was a grand science community. He taught me chemistry at Princeton. He was a brilliant guy and just so lovable. He was like a teddy bear. Well, when he was ready to retire and such, he passed the hat on to the third guy there. That's Don Herbert, who was America's science teacher, we called him. He was on television for 51 years, starting. He did over 4,800 television shows, programs in his thing. And every kid in the United States, I did, back in 1952, or 53, every Saturday morning we would watch Mr. Wizard on television just religiously. And one time they did a survey at NASA, this NASA engineers and astronauts and science people there. How many of you knew Mr. Wizard? And 66% of them said that Mr. Wizard is one of the key elements that got them interested in science. This was, back when television was young and probably had a better impact than it does today. But anyway, so I watched him when I was a kid. And then I started working for him in 1983, I think it was, when there was this new thing called cable television. And they came to Wizard and said, they're going to run cables to houses. And no, they'll never do that. And sure they did. They ran cable and so he was one of the first science education programs on cable, and that's when I went to work with him. He was getting older, needed a helper, and I was his helper for 25 years. And then at the Royal Institution, he passed the buck of being wizard to old Jake there. Look at that dark hair I had. Oh man, that's amazing. And remember that, Howie? You remember the dark hair? You remember that? It's been a while. It's been a while. So anyway, we have a collection of things. And when I came back from the Orkney Festival, I was so jazzed about doing something. What could I do? What could I do? Because I was at the festival and you sent me around to some schools, and those Scottish kids just sucked up, absorbed this stuff, and they just were fixated on it and mesmerized about this science, this hands-on science. And I thought, oh my gosh. So we pitched the idea, and the United Nations said, yes, we're doing these new goals, sustainability development goals, and we would like you to take this collection, turn it into something that we could share around the planet, especially to kids who are in underserved areas of the world. So we're saying, here are the future scientists who are now 10 years old. How old are you?
10 years old.
10 years old. How convenient is that? And so what we've done is we've gone through the collection, the Wizards collection, and I've got all of Faraday's stuff here, and Allier's and Don Herbert's stuff, and mine when I was on Discovery and stuff. And we cherry-picked those. We've gone through the collection and said, which activities will just captivate a young scientist's mind when they're somewhere between 10 and 14 years old. And they have to be activities that can be done at home with just things you'd find around the house, nothing special. And they will make a young person practice a science thinking skill while they're doing them, and they don't even know they're learning to be a scientist. They're just having a good time and learning a little bit of content, but they sharpen their thinking ability one little step at a time. So we started the Faraday 200, inspired by the Orkney Science Festival that I attended. I've been to 2 or 3 of them. I can't even remember. I'm getting so old, I don't know. Anyway, you inspired me, Howie. And so what I thought I would do today is show you 3 of the 200 activities, and we're growing them, we're polishing them there, and hopefully our goal is in 2023 we're going to be in Orkney, and we're going to have the official debut of the Faraday 200. We're going to stop in London and do the official ribbon cutting at the Royal Institution of Great Britain, and they're going to invite Prince Charles, and he's the patron now. We'll see if he shows up, but they never said we're going to start it there at the Royal, and then we're going to come up to Orkney and spend a week or 2 up there. So maybe this is a preview of 3 of these activities we've put together. And I don't think we developed them all, I think we've borrowed all. We didn't steal the recipes. I think we borrowed them from scientists and people around the planet. So can we just do that? Should we just do that? Should we just get started?
Excellent. Are
you awake, Howie? Are you awake? Did I put you to sleep yet? I don't. Yeah, you got to watch out. Howie is a good guy. He's a scientist, but he knows how to sleep with his eyes open. He taught me that trick. So let's see if I can wake Howie up with this activity. So here's the first one. I want to introduce Tristan. Do you have your glasses on? You have to have your glasses.
I do. Hold on.
This is Tristan. He's a member of Midnight Science Club, and over here I've got three of us here. And your name is what?
Ethan.
Oh, okay, that's right. His name's Ethan. Ethan, I've known Ethan for years. He's 10 years old. And sitting over the far distances, we call him Deuce. His nickname, we'll introduce Deuce anyway. Say something, Deuce.
Hello.
Hello, okay. So I've got 3 helpers, 3 members of the Midnight Science Club here with me, and we're gonna do 3 activities. So this first one I'm gonna do with Tristan. And Tristan's glasses inspired this one. Now Tristan's been hanging around here how many years?
3 at least.
3 years at least. And he wears these glasses that I will say are, well, I don't know, inspirational. And that made me think, those are kind of odd looking glasses, I thought, but I wouldn't say that to it. Oh, you heard me, I'm sorry. But I like your glasses, this is great. But they inspired me to pick this activity for the very first one at the Midnight Science Club. And so here it is. Well, let's see if we can read it. The first challenge of the Faraday 200 And these are for kids 10 to 14 years old. And the idea is we'll give one of these activities once a week for 4 years. So you'll do 200 activities spread over 4 years. And by the time you're done, you will have some science process thinking skills developed in your head and in your hands that you might not have otherwise. So the first one we're going to ask kids all around the planet to do is what?
Make a magnifying device and use it
Yeah, use it and describe how you used it. So I want you to make a magnifying device of any kind. Anything that will magnify, you make it, you put it to use, and then make notes of what you did. And that's it. Now the simplest one, of course, is, and you haven't seen this before, have you? Mm-hmm. No. I think the simplest one is just taking a drop of water. And if I take one drop of water and put it on something, you notice the shape it makes, right? What is that shape?
It's a little bead.
Little bead shape, right? It's got a curved surface, right? Yeah, a perfectly curved surface. That little drop of water, of course, you know, is a Leeuwenhoek. Is that how you say his name? Used a drop of oil to make the world's first microscope. And that little drop right there is a lens. You know, it'll bend light, refract light, and it will magnify. But I didn't want to spend time with a drop, so we cranked it up a little bit. I went down to the convenience store and bought a little laser pointer that fits on a keychain. You know, they're about $1.50, or you know what I'm talking about, a little keychain.
And little ones that
little ones like this. Now you've never seen this, right?
No, I have not.
You've not seen this. This man's been around, he hasn't seen it. So you recognize what I have here. This is my laser pointer that I picked up for a couple of bucks, right? There it is. And I've got a clothespin on there just to hold the switch on. That's all it is, right? And I've got it setting on this, this is called a lab jack. Now you don't have a lab jack at home, do you?
I have made one.
You've made one? Mm-hmm. Well, I did too. This is called the Howie Deluxe. I made it out of an old deodorant stick, and after it was used. And this is our homemade lab jack, in case you can't afford a $79 one, or wherever we got that one there. So Howie, I just want you to know this was named after you, the Howie deodorant lab jack substitute. But we're not going to use that. We're going to use the fancy one today. Anyway, I've got the laser pointer strapped to this little piece of metal, and this is our own design. You're going to have to design your own. You're going to have to take a laser pointer and figure out some way to shoot it through a drop of water. Now I've got an old syringe that I found, but you could use a medicine dropper, an eye dropper. And you can see, I don't know if you can see it, but I've got a drop of water hanging out of that syringe. And you could use an eyedropper, you know, if you had to. You could use a dropper. Now I'm going to leave it to you to design your own thing. This moves around. And I'm going to turn on the laser pointer. There it is. I'm going to aim it. I made it so I can aim it through the dot, through the little hole here at the drop of liquid. Okay. You're going to have to figure out your own design. I guess you could borrow my design, but you have to make up your own. Some way to get a laser pointer to shoot through a drop of water. And this is not drinking water. This is water I went down to the pond and got by the creek. There was a pond, and this has got pond water in it. And we know there are microorganisms in there, but we can't see those. So I found a box that I put a cardboard on, some white screen on, just so I can have something to look at. I think we're going to turn off the lights in here. Oh, now I don't know if you can see up here. Scott, show them what we recorded just a few minutes ago, would you? Because it's hard. It takes a. This is what you'll see. This was in our pond water, using our little laser pointer. Now, that's just a shadow. But it's amazing what you can see in a drop of pond water using our magnifying glass. So of course our challenge, the Faraday 200 is make some sort of magnifying device and then use it and make a record of what you see, what you observe. That's it. Isn't that amazing? A drop of water here in Kansas makes me want to go get a drink of water, doesn't it? I guess you get some extra vitamins if you drink that water.
Protein.
Protein. We get some extra protein there. Okay, that's one. Let's move over here. Thank you. Let's give Tristan a hand. The studio's got it, Tristan. I did most of the talking. I'm sorry about that. I do tend to talk too much, so I'm going to move over here next to my buddy. And what was your name again?
Ethan.
I knew that. I ask him that every time. Say hello, Scotland.
Hi, Scotland.
Hi, Are you Scottish?
No.
Okay, say Scotland.
Scotland.
He's got it. You've almost got it. So, let's see. The types of science that you've heard about: physics, chemistry, physics.
I said that first.
Yeah, physics, biology,
Yeah.
geology.
Yeah.
Yeah.
And then
There's pizzology, from eating pizza. Anyway, we're going to do a little chemistry. So, I found some chemicals around in the lab here. Do you have any chemicals at home?
if you count like vinegar or
You got
stuff
vinegar?
like your household stuff like carbon dioxide.
Yeah.
Well, not carbon dioxide, but we have.
You got a few chemicals around the house?
Yeah.
I bet there's one chemical you probably didn't know you had, a source of chemistry, or chemicals, and here they are, right here.
That's a grapefruit and that's an orange.
That's an orange, and that's a grapefruit. Yeah, there you go, man. They are, there's oranges. Oranges, by the way, and citrus fruits, I guess it's called citrus, and lemons, limes. Yeah, they're filled with mostly water, right? And a lot of sugar, juice in there and stuff like that. And a little bit of acid in there inside. But there is a chemical that's really neat that is in the skin of an orange, or any of these, I guess.
I had no idea.
Yeah, no idea. So I'm going to take this orange and I'm going to peel it a little bit. You say, man, Jake, this is not that exciting, peeling an orange.
It really isn't.
It really is. This is good, but it's like we are known for the amazing things we do here.
Yeah.
You say, well, an orange peel is amazing. Well, here's an orange peel. I'll give you a piece. Don't do anything with it until I get this other piece peeled. And I think this is a navel orange. It's got a thicker skin. Oh, what happened? Did you see that?
Yeah. What did you do?
What did I do? What was I doing?
You're peeling it.
Do you need to go to the restroom? Anybody? That scared me. That was terrible. I was peeling this orange, and the balloons are popping.
Yes, I had no idea.
You had no idea. Well, on the skin of that orange, the little pores, it's filled with a chemical called limonene. Say limonene.
Limonene.
Limonene, right? And for some reason, well, I know the reason. It interacts with the latex and breaks the cross-linking, right? It's a chemical reaction that takes place on the surface of those. So I want you to take your orange peel and just hold it over here over the top of these things. And when I say go, you.
I'm sorry.
Yes, let's try it again. Here we go. 1, 2, 3, go. Okay. Welcome to the festival here at Orkney. We're popping balloons with limonene spittle coming off the skin of this thing. So there is the essence of this activity. It's an old activity, and especially if you want to put a little limonene on your finger and then try to pick up a balloon and they pop, or water balloons or something like that. We're going to do. Did I get you guys over there on the other side of the studio? No. Okay. This is going to go on all day. So the challenge, Howie and folks, is, would you quit doing that? You're making me nervous here.
Yeah.
Are you doing that? Maybe a little bit. Because I want you to get some different citrus fruits that you get your hands on someplace. And especially if somebody's peeling it, you can just save the peel. So it's something that somebody would throw away. And go around the house with your parents' permission, of course, and test the effects of the limonene on various things. And see if there's any interaction. Do a little chemical testing with this limonene. And it's really fun when you find some latex, some non-vulcanized latex. And so you can torment the cat and your brother. I would show you some other things we can do because we're going to run out of time, but it's really fun when you have water balloons. You ever throw water balloons at your brother?
Yeah.
It's really kind of fun. If you can get your brother to handle and squeeze a piece of citrus fruit and then go pick up the water balloons. What do you think is going to happen?
It'll break in his face.
It'll break right in his face. This is what we do with some chemistry. So this is one of the Faraday 200. Do some chemistry. And I don't have any chemicals at home. Well, you do if you've got a piece of citrus fruit. And there's amazing interactions. So we challenge kids to find out what those interactions are. And balloons are one of them. I'm not going to give you all of them. There's a lot of neat things you can do with limonene. You did pretty good.
Thanks.
You can kind of keep up with the old man, can't you?
Yeah.
Can I trade places with you?
Sure.
Okay, thank you. So I've got to go over here and sit next to Deuce. And here's the third one. See, what's our first one? Our first one is make a magnifier and use it, keep track of it. Second one is get a piece of citrus fruit and perform some chemical tests or chemical interactions and make note of those. Just write notes of your observations. And the third one is, how you doing, man?
I'm doing pretty
Good to see you.
Good to see you as well.
Say hello to everybody in Scotland.
Hello?
You ever been to Scotland?
Nah,
You know?
haven't been outside the country.
Really?
Not yet.
Yeah, they did impact our town here.
Yours doesn't work. How so?
They sent we have a great Scottish restaurant here. We got several of them in town. They had the big golden arches, that McDonald's. That didn't go down. Okay, never mind. Never mind, I tried, but that was about as good as it gets here. So I'm afraid to touch these balloons now that I've got limonene all over them. So would you pick up the balloons? Thank you. So this is our festive part of the festival here. We're going to try this thing. The third challenge to Faraday 200 is to do something amazing with a stream of air. Of course, it's basic aeronautics is what we're going to try to get across. Do something amazing with a stream of air. Now I say, well, I don't have an air stream. What do you mean stream of air? So you probably got a hair dryer at home or a vacuum cleaner and the exhaust of a vacuum. You got some source of moving air. I want you to find that source of moving air. And you have to, we want to straighten it out. And I don't know if you can see this or not, but I've got a little blower here. And I've got, it's like from a vacuum cleaner. Right there it is. And I filled this tube with soda straws that act like straighteners. Let's see if I can tip that so you can see that. Can you see that at all? Let me see here. Can you see the soda straws down in there? I don't know. Yeah. You got those? Yeah. See them good? Cool. I stuffed that little pipe with soda straws just to straighten out the air so it won't come out spraying. It comes out. So now I've got a stream of air. So the third Faraday 200 challenge is establish a stream of air somehow with things you find around the house. I don't know what you've got. Hair dryer, paint blower, I don't know what would be. And see if you can do something amazing with it. And if you can, I want you to draw a picture of it and describe your observations. That's all you have to do. Just describe your observation. You don't have to know everything that's going on, but I want you to make an airstream out of something. I suppose it could just be a straw. That'd be an airstream, yeah. Do that. See if you can do something amazing with it. And then I want you to write your experiences, make some notes, and that's all you have to do. You know, probably take you, how long would it take you to do all that?
Depends on the day.
Depends on the day, okay. So I've got the blower here, and I've got it connected to a switch. I'm going to turn it on. Is this thing going to fire up here? Oh, wrong one. I put mine on a dimmer. Now you've probably seen this everywhere. Have you ever seen a balloon or a ball suspended in an airstream? You know, yeah, that's pretty simple stuff, right? And that, well, here, let's try it with the one balloon first. Here, lay that down. I'm afraid to touch them. I'm afraid I'm going to pop them. Here, I can hold the top right there. I'll turn this on. Let's see if you can get that floating in that airstream. Sweet. The airstream is, yeah, the pressure is increased here and it's lessened on the outside. You know? So there that is. That's not, you've seen that before, right? Okay. So Howie, in the honor of the Orkney International Science Festival, we came up with the Orkney O Deluxe balloon demonstration. Are you ready for this?
Well, I'm ready.
Okay, I'm going to turn it on. Let's put it on. We've got a ring of balloons. Well, how many is that? That's 6 balloons, is it? Okay.
Yes, sir.
Got 6 balloons and they're connected together. And we're going to see if we can do a little aerodynamic delight here. And of course, when kids do this, they're going to have to describe, part of the challenge is, well, what's that air doing? Why is this balloon doing what it's doing? And I just want you to think about it, not for very long, just a little bit, and then write that down. So here we go. Here we go. You ready?
I'm ready.
Okay, let it go. Put it in there. Okay.
It went too far.
Okay. Might have to turn it up a little bit. Okay, where's it going? Got to turn it down a little bit. Here we go. You grab it. Why don't you stand up and I'll sit here. Try to look. Turn it down a little bit. Now hold it straight up and down. So, look, yeah, hold it like that. Now let it go. Okay.
There we go. It's spinning.
Welcome to the Orkney International Science Festival, the Big O. There it is. Look at it. It's going now. We got it. We've got it. I'm going to turn it up just a little bit.
Oh, it's spinning.
Yeah, it's spinning. Okay. Supposed to be 7 balloons. I think 7 balloons works better. There it is. There we go. This is 6. I'll turn it down a little bit. Let's try it one more time.
It's a little way.
Yeah, try it one more time. We're going to get it right. There we go. There we go. I think we have it. I think we have it, ladies and gentlemen. Are you pleased? Give me a thumbs up. Give me a thumbs up. All right. Enough of this. Thank you, dude. Appreciate it. Let's go back over here. Grab your fuel. We've got it going now. There we go. Watch out. All right, turn it off. Here we go. Well, you can see that the science is not really that deep, except the skill building is to get a young person to describe in their own words what's happening is the essence of scientific thinking. So why did that stream stay the way it did? And I'm not going to ask you to answer that now, but why? What was the air doing? Getting it in there is kind of difficult to do once you finally get that built. But you could do it with a ping pong ball and a hairdryer. You don't have to use balloons. So I guess we're ready for some questions, Howie. Is that what we do?
That's it. Now, I'm going to ask, in fact, that is so fascinating. A number of questions have come in, but I'm also going to ask Katie, Connie, Emily, Emma, and Vasilius to join us as well, because a question has come in that I think we can put to all of you. I'll tell you what the question is first and give you a moment to think about it. If you were to have the opportunity to invite a particular scientist from history to come and join you this evening for this session or to chat afterwards, who would you pick? And while you're thinking about it, I'll just ask John to show that Slido link again so that anyone watching with their mobile phone knows how to send questions into us. And this will apply right throughout the festival. There it is, slido.com, and the code is 343. So here we go with our question then. And this time it's quite a short answer. See if you could do it in a minute. And I'm going to go to Vasilius first. Choose your scientist who you would like to join you and chat with afterwards.
Good question. There's so many that come to mind. But since I've been talking about the Antikythera mechanism, one of the prime contenders for designing this mechanism is a guy called Posidonius. He lived around about the time that the mechanism has been dated to. He was a polymath. He lived in Rhodes, which is for various reasons where we think the mechanism may have been built. So he is the guy I would have liked to to have with me this evening and ask him all about the secrets of the mechanism, the ones that we don't know yet.
He would be fascinating company. And Katie, you now have a choice as well.
So we were just thinking, just because he's right here next to us, I'm going to turn my camera around. Can you see Hugh Miller? Yeah. We'd like to invite Hugh Miller because we have one of his discoveries here in the museum, and I would love to ask him more about how he discovered it around Stromness, since it was just on our doorstep.
Again, that would be fascinating company. Now, Emma, how about you?
Yeah, so I've slightly stolen my Hugh Miller one there, famous paleontologist there. I think I would love to have a conversation with Mary Anning. She's a very famous female paleontologist back in the day when women weren't allowed to do science or to get involved. So I would love to know about her going out there, finding all these different fossils down in Lyme Regis in Dorset, and have that conversation with her.
And Jake, how about you for a guest?
It'd have to be Faraday, and I don't think it would be a scientific question as much as he worked so hard at what he did, hour after hour after hour, on some of the projects, you know, wrapping wire that he had to make the insulation for and tying little knots for endless hours. I would want to know how he kept his mind focused and didn't give up and wear out and burn out and all that stuff. That his work was magnificent, but the amount of tedious work that he had to do, I said, how did you beat that challenge? Because I'm getting old and I want to retire, I think, and it's like, you know, how do you keep going?
Well, it's been a pleasure to be joined in you all this evening. What a great start you've got us off to, looking at a computer from the seabed, looking at ancient fossils from fish that swam in a long ago lake, and doing all sorts of wonderful things with balloons. Thank you indeed to Vasilius, to Katie, to Connie, to Emily, to Emma, to Jake and his team there. We much appreciate your company. I should just say for viewers that tomorrow we'll be in person in the Phoenix Cinema at 11:30. Our topic will be engineering the future. We'll look at the new science of transition engineering and the opportunities it gives for tackling global challenges with practical solutions. In the meantime, to all our team on screen, to the team behind the screen who've flowed everything so smoothly, and to viewers wherever you are, thank you very much and good evening for now. Bye.